I am recording now. Thanks. And we started looking at right triangle trigonometry last time. I want to make sure that we're all good with this, so we're going to kind of review everything. We looked at the Pythagorean theorem that the legs of a right triangle, that's the vertical and horizontal parts, if you square those distances and add them together, you'll get the square of the third side, which is called the hypotenuse. And before we look at these fun trig identities, I want to play with. We did this one, didn't we? This example? Or did we finish it?
I don't remember.
I don't either.
Yeah, I'm not sure.
I think we did. So I'd like to do, this one was a try this, but I'd like to do this one with y'all. Just because it's just fun to play with. Actually, I keep flipping all over the place, sorry. So let's do this one, because this one has fractions, and fractions are probably everyone's biggest joy. So we're going to example 3, and I'm just gonna label, because I'm boring, A is always gonna be the horizontal part, B is the vertical, and C is the hypotenuse. And how can we find B?
Set it up as an equation.
Okay, good. So we know that A squared plus B squared equals C squared. Now what?
So then we fill in our values. So 3/5 plus B squared equals 1.
All right. And I'm just putting everything in parentheses to get used to that. It's better to have them and not need them than to need them and not have them.
Yeah.
So now if we square 3/5, that'd be 9/25. And then we could subtract that from 1, and then that'd be our answer for B squared, and then just take the square root of that, right?
Yeah, so let's see, we've got B squared is 1 minus 9/25. And how can we combine those fractions? Well, they're not both fractions.
Can't you rewrite 1 as 25/25?
Very good. Everybody in the chat thing,
So that should be 16.
tell me why this is a good thing to do. Everybody tell me. You can send it just to me, or you can send it to everyone, but I want everyone to tell me why replacing 1 with 25/25 is allowed and why it's a good thing to do. And so far I see 0 people. There we go. Hey. Yes, good. Good. And not only do we have a common denominator, but why can 1 look like 25/25?
Because it still equals out to what?
That's right. That's right. 25 divided by 25 is 1. So yes, now we've got a common denominator. And how do I deal with that? Remind me.
It would just be 25 minus 9.
Yeah, 25.
Beautiful. Now what?
So that would be, I'm pretty sure 16 over 25. And then if we just take the square root of that, then we'll get b.
And what was I sort of emphatic about including at this step,
Plus or minus.
plus or minus, every time, every time? Let me see if this is from a student. Okay. No, wasn't. So square root of b squared is b. Why do I not need the plus or minus at the next step?
Because we're measuring length, and length can't be negative.
Good. And I'm going to go ahead and put this here still. How do you take the square root of a fraction?
You take the square root of the numerator and the square root of the denominator.
Beautiful. And square root of 16.
Is 4.
4.
Yay. Square root of 25.
5.
Beautiful. So let's go back to our sketch. And I wanted to get you thinking, I guess. A triangle can have really weird lengths for the legs and have a unit length for the hypotenuse. I'm going to pause the video. I want y'all to do this one, and it's not 5 and, well, this is 5 over 13. And remember that y'all are supposed to talk to each other. Beautiful. And now let's do the try this together. So try this number 2. Let's see if, just as a review of dealing with square roots. So we know that the horizontal side is square root of 6 units. We do not know the vertical side, and we know the hypotenuse is 3. How can I, what can I do?
So I would start with squaring the square root of 6 and 3.
Okay, and we're labeling like this. A is the horizontal, B is the vertical, and C is the hypotenuse. Yes?
Yes.
I would like y'all to start to get into the habit of writing down the rule before you put in numbers, because we're going to have more and more complicated rules, and this is just a good habit. So we've got square root of 6 squared plus b squared is 3 squared. And just like Ben said, what is square root of 6 squared?
6.
Beautiful. And 3 squared? I almost said what it was.
Is 9.
Okay. And now what?
And now if we just look at it, it's decently obvious that b squared would have to be 3.
Well, let's be painfully, let's show this in painful detail. So yeah, so b squared is 3. And now what?
Since there's no, like, I guess actual number that is squared to get 3, it would have to be square root of 3.
Okay, but what do you have to do at this step?
Plus minus.
Yeah. Square root, plus minus. Now start thinking. So square root of b squared is b. Now we can say we don't need the plus or minus, and now we can say that square root of 3 is just itself. And it kind of makes sense. Square root of 3 squared is 3. 6 square root of 6 squared is 6. 6 plus 3 is 9. Square root of 9 is 3. Oh, well, we didn't finish. Good, I'm glad, because I was thinking that went by awfully quickly. Okay, so now let's look at our prettier version. Sorry about pulling out the one that we've already written on. Okay, I guess this is fine. So we've got sine is defined to be. These are definitions. This is not something we're supposed to wake up knowing. This is a definition. Whatever sine is, we find it by, it's always associated with an angle, and we find it by taking the side opposite, that length, and dividing it by the hypotenuse, that length. That is the definition of sine of theta, where theta is the angle we're referring to. So let's find the sine of, let's find the sine, cosine. Well, let's just first start with the sine of these two angles, these two triangles. If theta is this bottom angle, what was the quotient to find sine? What is the ratio?
Opposite over hypotenuse.
Good. And the side opposite associated with theta, so opposite, is
Square root of 3.
beautiful. And the hypotenuse,
3.
beautiful. Cosine is defined to be adjacent over hypotenuse. And adjacent is always a leg. Opposite is always a leg. Well, for this triangle, what is the adjacent length?
Square root of 6.
And the hypotenuse is still 3. And then we have one more primary ratio, and that's called the tangent. And tangent of theta is defined to be opposite divided by adjacent. Well, in this case, opposite is
Square root of 3.
adjacent.
Square root of 6.
And here, we're not as simplified as we could be because we have two root symbols. So how do we rationalize, in other words, how do we get rid of one of those root symbols?
Do we square the fraction?
We can't square the fraction because that will change it. But we're going to do something similar. We're going to square the denominator and then multiply the numerator by that same value. So square root of 3, I mean, square root of 6 times square root of 6.
6.
And let's multiply mindfully. We've got 3 times 6, but 6 is what times what?
3 times 2.
6 is 3 times 2. So we've got 3 times 3 times 2. And why did we do that? Why is that a good thing? Or even a thing?
That's another way of writing out square root of 6. That doesn't change the fraction.
Okay. And does this lead us toward any kind of simplification?
Yeah, it would.
Okay, tell me.
Because 3 times 3 is 9.
Okay. So
And
let's
then
together. And then
9 times 2 is 18.
good. And square root of 9?
Square root of 9 is 3.
3.
And now?
Now would we cancel out the 3 with the 6, and then the 6 would just be left with 2?
Yeah, so 3 goes into 3 once, 3 goes into 6
Twice.
twice, and we're left with square root of 2 over 2. Isn't that beautiful? So do you see that this time we had a result, square root of 3 over square root of 6, and we were able to make it look simpler, truly simpler, not just move a square root somewhere. But we have one root symbol in the answer, and the answer is simpler. So I'll explain now why I harp on Alex will make you rationalize every denominator. In other words, Alex will not accept an answer if there's a square root symbol in the denominator. It will say it's wrong, which, anyway, we know that sine of theta is opposite over, what was it? Opposite over,
Hypotenuse.
oh, thanks. Cosine is
Adjacent over hypotenuse.
tangent
Opposite over adjacent.
beautiful. And if you think of a triangle, we are only halfway to all the possible ways we could take the sides and divide them. The other ways are the reciprocals of these. So we could have hypotenuse divided by opposite. We could have hypotenuse divided by adjacent, or we could have adjacent
Divided by opposite.
good. Thanks, Ben. This first one is the cosecant. CSC of theta.
Okay.
The second one is the secant of theta. And the third is the cotangent of theta. And what you can see is that cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. cotangent is the reciprocal of tangent. So let's use that, this information and the values that we just found. See, we said that the tangent was square root of 2 over 2. We said that the cosine was square root of 6 over 3, and that the sine was the square root of 3 over 3. And what we're going to do now is talk about reciprocals. So I've had many students take this and do this to it. 1 over square root of 3 over 3. And that's not wrong, but it's extra. If I have the reciprocal of a fraction, how do you find the reciprocal of a fraction?
And just switch the numerator and denominator.
Exactly right. So we just have 3 over square root of 3. Then what about the reciprocal of cosine?
3 over square root of 6.
And reciprocal of tangent?
2 over square root of 2.
These are the answers I would want. And in your future classes, these are the answers that will be best because they're most useful. But Alex will not accept them. And Alex will say they're wrong. It won't just say it's the wrong form. It'll say it's wrong. Anyway, so let's practice rationalizing. Rationalizing, write that down, rationalizing. Is the process of moving a root symbol from denominator to numerator or from numerator to denominator. We'll do both in our class. Okay, how can we rationalize 3 over the square root of 3? Evelyn?
You take the square of the denominator.
Yes. And what do we do in the numerator?
Would we multiply both sides by the square root of 3, or would we square both sides?
No. So
Okay, that makes sense.
we can think of squaring the denominator as long as we remember that that means we multiply the numerator also by the square root of 3. All right. Well,
Oh, so it's just multiplying by 1 to change the form.
that's right. That's right. To move the radical, the square root symbol from the bottom to the top. And this time it is actually going to simplify. So this is nice. So let's see, in the numerator, we've got 3 square root of 3. What do we have in the denominator?
Just 3.
And
Square root of 3 over 3.
say it again.
I'm sorry, I was
Oh, because
talking about the math.
3 goes into 3 once and on both sides.
Yes. So we're left with square root of 3 for the cosecant, which is very nice, actually. And we've got 3 over the square root of 6 for the secant. Let's rationalize that. So somebody tell me exactly what I'm multiplying numerator and denominator by.
So you're multiplying the denominator by square root of 6 because you're squaring it.
Mhm.
And then you're also multiplying the numerator by square root of 6.
And in the numerator, we'll have
3 square root of 6,
beautiful, and in the denominator.
just 6.
And now,
3 goes into 3 once, and 3 goes into 6 twice.
so we're left with square root of 6 over 2. And that is a pretty answer. They're both valid, but this one is pretty, so it's not a waste of time. And in fact, we're going to see the same thing happen here again. So help me rationalize 2 over the square root of 2. Somebody who hasn't helped. Evelyn?
You said this 2 and square root of 2. We're trying to rationalize this.
Yes.
Multiplied by the square root of 2.
So in the numerator, we have
2 times the square root of 2.
beautiful. And in the denominator,
2.
and
Then 2 and 2 gets, I guess, cancel, and then you put square
we
root of
put
2.
it 2 once, 2 goes into 2 once, and the one in the denominator is not necessary. Yes, yay, beautiful. So I want y'all to play that same game. With actually, let's do this one together, and then y'all, since you already figured out that the third side of the triangle here was 12/13.
Yep.
You're going to find the 6 trigonometric ratios for that triangle after we do the same thing with this one. And I trust that if you're not understanding, you'll either message me or text me or something so that I can pause. And I will not say, I'm pausing because Ben asked the question. I will not do that. Okay, so we have the triangle. Four-fifths, three-fifths, 1. And we want to find the sine of theta, the cosine of theta, the tangent of theta, and the reciprocals. Okay, and sine is whatever what?
Opposite over hypotenuse.
And opposite is?
4 over 5.
Hypotenuse.
1.
So what is the sine?
4 over 5.
Good. Cosine is defined to be
Adjacent over hypotenuse.
beautiful. If I repeat something like this or ask it over and over, I really do want you to know that. I don't want you to remember it. I want you to know it. Okay, so what is the adjacent side?
3 over 5.
And the hypotenuse.
1.
So that the cosine is
3/5, sorry.
Beautiful. And tangent is going to give us a nice opportunity to look at a technique we're going to use when things get really fun. So the tangent of theta is defined to be,
Opposite over adjacent.
beautiful, and let's see. So I've got tangent theta equals. Opposite is
4/5.
and adjacent.
3/5.
3/5.
We could take this middle bar and change it from a bar to a division symbol, and then first fraction, change this to a multiplication symbol, flip the second, but there's a much, much better technique. And that technique isn't necessary here, but we're going to use the technique later. So we're going to look at both of the inside fractions, and the denominator of the first inside fraction is,
5.
and the denominator of the second inside fraction is,
5.
and what's the least common denominator between 5 and 5?
5.
We're going to multiply numerator and denominator by the least common denominator of the inside denominator. And instead of multiplying, we're going to divide. We have 4/5 times 5, 3/5 times 5. And what do I mean instead of multiply, we're going to divide? Ethan?
I don't know.
Ben?
Yeah, I'm not sure either.
Okay. So 5 is the same as 5/1, yes?
Yes.
So 5 goes into 5.
5 times. Wait, no, sorry. 1 time.
And 5 goes into 5.
1 time.
So we're left with, in the numerator,
Oh, okay.
good. And what happens in the denominator?
The same thing.
And we're left with,
3.
so that technique of taking a complex fraction and making it a usable regular fraction in one step is nice when we've got fractions with numbers, but we're going to have pretty complicated fractions with trig stuff. And it'll be so wonderful to take a huge, horrible thing and in one step have something that's pretty and more usable. Okay, so the tangent is 4/3. The sine is 4/5. The cosine is 3/5. Tangent is 4/3. What is the cosecant?
5/4.
Beautiful. What is the secant?
5/3.
And what is the cotangent?
3/4.
3/4.
Beautiful. And the way that you can remember which thing goes with which other thing is that tangent and cotangent go together. That's kind of easy. And the others, sine goes with the one that's a cosine goes with the one that isn't. So there's always only one cos. in each. Cosine goes with secant, cosecant goes with sine. Chris,
Hmm.
does that help?
Kind of.
So all of this stuff, what I mean when I say I don't want you to remember it, I want you to know it. I want when you have Alzheimer's and you've forgotten your children's names and you pet your dog, but you don't know who he is, I want you to remember to know, oh, the reciprocal of tangent, it's cotangent. You just take the fraction. Yeah. All right, I'm gonna pause the video and y'all are gonna do